If we think about everything which surrounds us, the technology, the laws of physics that describe what happens in nature, we can use them, we can do something with them. We have the technology that we have because there is mathematics. Mathematics has been the way for the human to understand phenomena.
That in fact, by now there are in fact many parts of mathematics which have become interesting for applications. So many more than a few decades ago.
应用往往是一门综合学科 ，even 在数学里面，你要解决一个应用数学解决问题，你不是一个单门的理论数学可以解决，这实际上是一个系统工程，数学的系统工程。
So we are at a moment where I think the computational power, it's really at the maximal level, maybe a bit better, but nothing exceptional. It's not going to be like 1,000 times better. But mathematically, as I say, there are many challenges, and I think once we will understand better how AI works, why it works, how to improve it, how to make it more efficient, safer, and everything, this is when we will see a next revolution.
I mean, if you have theory but without practical case, so you find, you kind of lose a sense of purpose. Whereas, here, if you do also the practice but without a good theory, well, you will continue on improving already known techniques, but you will not do something revolutionary. I mean, of course, you will advance the technology, but basically you will be in the same trend. I mean, we'll just add some new layer of refinement, but it will not be a step forward somehow.
So we think that, of course, when you are a theoretician, you are looking for understanding. But when you are an engineer, you are looking for something which works better. But then there is a miracle that usually when you get better understanding, you become more efficient. So here what we need is in some sense to enrich the amount of mathematical knowledge of the computer scientists we talk with in order to make them realize that they can try to implement larger schemes.
就比如说是像那个大型语言模型，它里面最基础的模块是 transformer。transformer 实际上基本来说90%以上都是矩阵运算。这些矩阵运算我们如何给它加速？如果说我们能够加进很多数学的东西，就比如说利用好的矩阵分解、张量分解，利用比较好的核函数的设计，以及利用比较好的那个位置编码的方式，我相信是可以更有效的去加速整个大型语言模型的计算。
I studied mathematics. I developed new methods for solar physics. And then during conferences, I met people from cardiology. They showed their time series, their measurements, and looked very similar as solar activity. And then this is a way of interdisciplinary. Then we talked with each other and worked with each other. But the important point is Each discipline has its own language, specific language. And the problem is that you have to learn, each side has to learn a bit the basic parts, not complete, but basic parts of the language of the others, that we really can communicate and that they can tell what are their real problems.
比如说可以从黄大年开始，你比如黄大年可以提供一系列的数学的课程，比如说是一些跟那个 AI 相关的数学，或者说跟其他方面，跟研究物理、跟材料、化学都需要不同的数学。从最简单的方程式开始，慢慢一步步的把这个问题给解剖开来，往深的方向走，就看你的兴趣。觉得要有一个好的一个提供知识的平台，我觉得需要形成一个这样的机制。数学是最赤裸裸的东西，它直接告诉你一个事情的一个现象的本质，背后的本质是什么。
And mathematics is really something that once you understand it, you can see the beauty of it. You can see the kind of creativity. For some things it's like art. If we think about everything which surrounds us, the technology, the laws of physics that describe what happens in nature, we can use them, we can do something with them. We have the technology that we have because there is mathematics. Mathematics has been the way for the human to understand phenomena.
That in fact, by now there are in fact many parts of mathematics which have become interesting for applications. So many more than a few decades ago.
应用往往是一门综合学科，even 在数学里面，你要解决一个应用数学解决问题，你不是一个单门的理论数学可以解决，这实际上是一个系统工程，数学的系统工程。
So we are at a moment where I think the computational power, it's really at the maximal level, maybe a bit better, but nothing exceptional. It's not going to be like 1,000 times better. And but mathematically, as I say, there are many challenges, and I think once we will understand better how AI works, why it works, how to improve it, how to make it more efficient, safer, and everything, this is when we will see a next revolution.
I mean, if you have theory but without practical case, so you find, you kind of lose a sense of purpose. Whereas, here, if you do also the practice but without a good theory, well, you will continue on improving already known techniques, but you will not do something revolutionary. I mean, of course, you will advance the technology, but basically you will be in the same trend. I mean, we'll just add some new layer of refinement, but it will not be a step forward somehow.
So we think that, of course, when you are a theoretician, you are looking for understanding. But when you are an engineer, you are looking for something which works better. But then there is a miracle that usually when you get better understanding, you become more efficient. So here what we need is in some sense to enrich the amount of mathematical knowledge of the computer scientists we talk with in order to make them realize that they can try to implement larger schemes.
就比如说是像那个大型语言模型，它里面最基础的模块是 transformer。transformer 实际上基本来说90%以上都是矩阵运算。这些矩阵运算我们如何给它加速？如果说我们能够加进很多数学的东西，就比如说利用好的矩阵分解、张量分解，利用比较好的核函数的设计，以及利用比较好的那个位置编码的方式，我相信是可以更有效的去加速整个大型语言模型的计算。
I studied mathematics. I developed new methods for solar physics. And then during conferences, I met people from cardiology. They showed their time series, their measurements, and looked very similar as solar activity. And then this is a way of interdisciplinary. Then we talked with each other and worked with each other. But the important point is each discipline has its own language, specific language. And the problem is that you have to learn, each side has to learn a bit the basic parts, not complete, but basic parts of the language of the others, that we really can communicate and that they can tell what are their real problems.
比如说可以从黄大年开始，比如黄大年可以提供一系列的数学的课程，比如说是一些跟那个 AI 相关的数学，或者说跟其他方面，跟研究物理、跟材料、化学都需要不同的数学。从最简单的方程式 开始慢慢一步步的把这个问题给解剖开来，往深的方向走，就看你的兴趣。也要有一个好的一个提供知识的平台，我觉得需要形成一个这样的机制。数学是最赤裸裸的东西，它直接告诉你一个事情的一个现象的本质，背后的本质是什么。
And mathematics is really something that once you understand it, you can see the beauty of it. You can see the kind of creativity. For some things it's like art. If we think about everything which surrounds us, the technology, the laws of physics that describe what happens in nature, we can use them, we can do something with them. We have the technology that we have because there is mathematics. Mathematics has been the way for the human to understand phenomena.
That in fact, by now there are in fact many parts of mathematics which have become interesting for applications. So many more than a few decades ago.
应用往往是一门综合学科 ，even 在数学里面，你要解决一个应用数学解决问题，不是一个单门的理论数学可以解决，这实际上是一个系统工程，数学的系统工程。
So we are at a moment where I think the computational power, it's really at the level, at the maximal level, maybe a bit better, but nothing exceptional. It's not going to be like 1,000 times better. And but mathematically, as I say, there are many challenges, and I think once we will understand better how AI works, why it works, how to improve it, how to make it more efficient, safer, and everything, this is when we will see a next revolution.
I mean, if you have theory but without practical case, so you find, you kind of lose a sense of purpose. Whereas, here, if you do also the practice but without a good theory, well, you will continue on improving already known techniques, but you will not do something revolutionary. I mean, of course, you will advance the technology, but basically you will be in the same trend. I mean, we'll just add some new layer of refinement, but it will not be a step forward somehow.
So we think that, of course, when you are a theoretician, you are looking for understanding. But when you are an engineer, you are looking for something which works better. But then there is a miracle that usually when you get better understanding, you become more efficient. So here what we need is, in some sense, to enrich the amount of mathematical knowledge of the computer scientists we talk with, in order to make them realize that they can try to implement larger schemes.
就比如说是像那个大型语言模型，它里面最基础的模块是 transformer。transformer 实际上基本来说90%以上都是矩阵运算。这些矩阵运算我们如何给它加速？如果说我们能够加进很多数学的东西，就比如说利用好的矩阵分解、张量分解，利用比较好的核函数的设计，以及利用比较好的那个位置编码的方式，我相信是可以更有效的去加速整个大型语言模型的计算。
I studied mathematics. I developed new methods for solar physics. And then during conferences, I met people from cardiology. They showed their time series, their measurements, and looked very similar as solar activity. And then this is a way of interdisciplinary. Then we talked with each other and worked with each other. But the important point is each discipline has its own language, specific language. And the problem is that you have to learn, each side has to learn a bit the basic parts, not complete, but basic parts of the language of the others, that we really can communicate and that they can tell what are their real problems.
比如说可以从黄大年开始，比如黄大年可以提供一系列的数学的课程，比如说是一些跟那个 AI 相关的数学，或者说跟其他方面，跟研究物理、跟材料、化学都需要不同的数学。从最简单的方程式开始，慢慢一步步的把这个问题给解剖开来，往深的方向走，就看你的兴趣。觉得要有一个好的一个提供知识的平台，我觉得需要形成一个这样的机制。 数学是最赤裸裸的东西，它直接告诉你一个事情的一个现象的本质，背后的本质是什么。
And mathematics is really something that once you understand it, you can see the beauty of it. You can see the kind of creativity. For some things it's like art. If we think about everything which surrounds us, the technology, the laws of physics that describe what happens in nature, we can use them, we can do something with them. We have the technology that we have because there is mathematics. Mathematics has been the way for the human to understand phenomena.
That in fact, by now there are in fact many parts of mathematics which have become interesting for applications. So many more than a few decades ago.
应用往往是一门综合学科 ，even 在数学里面，你要解决一个应用数学解决问题，你不是一个单门的理论数学可以解决，这实际上是一个系统工程，数学的系统工程。
So we are at a moment where I think the computational power, it's really at the maximal level, maybe a bit better, but nothing exceptional. It's not going to be like 1,000 times better. But mathematically, as I say, there are many challenges, and I think once we will understand better how AI works, why it works, how to improve it, how to make it more efficient, safer, and everything, this is when we will see a next revolution.
I mean, if you have theory but without practical case, so you find, you kind of lose a sense of purpose. Whereas, here, if you do also the practice but without a good theory.
You rested, slept well. So we are, after a long day yesterday, we're coming back to second part from Alexander. So please enjoy the second part.
Thank you very much for the introduction. Can you hear me well? Is it working? Okay. So let's see where we finished yesterday. Okay, let's first recall the basic properties just to remember what we have. So the basic properties of tensor product are listed here. And this is what we are going to use. These are basically the only properties that we are going to use in the next application that I'm going to show. So this was the solution of the first problem. I just wanted to mention quickly that if you try to construct the Hadamard matrix, you can try to do it on your own. Maybe it seems a bit too trivial when you see the answer. But if you try to construct it on your own, you will see that it's not that easy to do it. So have in mind that this is not the hardest application. This is obviously trivial if it has just a few lines of proof. But if you try to do it by hands, you will have to construct something recursively, and then you will basically end up doing exactly this. So we're going to show another application of tensor products, and this is the basic question of you've all eaten a chocolate at some point. Let me just increase the size. Okay, so you have a chocolate, and you know that you have some, we call it kockice in Croatian. It's cubes, but they are not actually cubes. They are like little squares of some thickness. But you know, if your chocolate has dimensions of, let's say, 2x and this is 3x, and this is 1, 2, 3, 4, 5x. Whatever x is, you can make such a decomposition. So you can divide the chocolate into 15 little squares, right? It doesn't matter if this x is rational or irrational. Okay, so the only thing that you need to consider is the ratio of side lengths. So because 5x over 3x is element of Q, we know that we can decompose the chocolate in such squares. This is a simple problem. You can try to do it on your own, and you will all certainly be successful in this. This is a very simple problem, and you were competitors, most of you, so this is a simple problem. Now, the question is reverse. So if we know that some rectangle can be decomposed into squares, do we need to have, so now if we have some length A and some length B, and if it can be decomposed into squares, is it necessary that A over B is a rational number? So this is the question that we are going to solve. And now if we try to approach this problem without tensor product, you will have a hard time, like if you just consider areas or something like that. The main point of solution is that like area is a product of two lengths, but we would like to choose something that is that is not exactly a product. That we will see. We would like to choose another bilinear form which will separate the case when this can be decomposed into squares and when it cannot. Let's see what can we do. So we know that some decomposition into squares exists. We do not know what it looks like. It can look sorry. Suppose that this is square, then another square can be adjacent to this one in this way, and then, so imagine that there is no room here. I'm not able to draw that so well, but yeah. Imagine that we have some decomposition into squares, and we do not know what it looks like. It doesn't have to be this one. There is some decomposition into squares, and we want to prove that then sorry? No, they do not have to be of the same size. Just any squares. So we would like to prove that it's necessary for these side lengths for their ratio to be rational. So what do? We enlarge these sides to take all the parallel lines with the grid and observe the following result. So this is like the composition with all sides. I think now I'm missing this one. And now the first observation is that we have some side length. This is like x1, this will be x2, this will be x3, this will be x4 in this, and this will be x0. And now, what do we know? We know that like when you decompose things like this, then you know that area must be preserved. Like when you decompose some shape into little, sorry, I'm also missing this one. And let's say call this epsilon, y1, y2, y3, y4, y5, y6, and this is y0. We know that area is preserved, but something more is preserved. And this is, what is preserved is a tensor product structure. So if we can do this, if we separate all the separate the plane with little rectangles, we know that if we form them back into a square, okay, if we can arrange them back into a square, then using this simple bilinear observation, we will have that rectangle, any rectangle is going to be sum of little rectangles. So something more than just an area is preserved. If this was a product here, standard product, this would say that if I have area divided into little rectangles, it is preserved upon taking everything back and summing the areas of little squares. But if I take tensor product of these things, then also the tensor product is preserved. But where is this tensor product defined on? This is the question. So we would like to say that something is inside the Q, and you've heard yesterday about some vector spaces in Professor Kazalitsky's lecture and Dr. Ivan Novak's lecture, that there are some vector spaces that appear naturally over the field Q. For example, if I write this Q expanded with a square root of 2, this is the set of elements a plus b square root of 2. where A and B are rational numbers. This is a vector space over rational numbers. Its dimension is 2 because we have a Q and we have another vector which is not in Q. So if I take all these x's and y's and I form the vector space with all x's and all y's, sorry, x0, y0 to yn, should be m, then this is a vector space over Q. Okay, this is a vector space over the field Q, and we can work everything in this finitely dimensional vector space. The basis is the smallest number of these numbers needed to have expression, to have a basis for this vector space. So everything is finitely dimensional. We can take a Hamel basis, if you've heard of that, to even have simpler life without doing all these steps. We know that real numbers are vector space over Q, but we do not need this in this solution. So we can just take a vector space of this shape. So what do we observe? In this vector space, we have a tensor product because we have a vector space. This is why we wanted a more general approach without referring to some coordinatization or anything. Now we know we have a vector space, tensor product is well defined. And now this tensor product is preserved under such decompositions. So if we decompose everything into these little rectangles and then form back these squares that we had, I can draw with another color. So if we know that we can turn everything back into squares, then by using this observation, we observe that one needs to have that A O times B is tensor product of length of little squares. So these CI's are these differences of x2 minus x1 and so on. Okay, so this is, I'm again repeating that if this was just an ordinary product, this would just mean that area of a rectangle is sum of little areas of squares. But we have more than that. And now if we just choose bilinear form or linear functional on the space of tensor products, we can choose, if suppose that A and B are not rational, then we can choose, for example, in this case, we can choose a linear operator such that L of square root of 2 is equal to minus 1 and L of 1 is 1, for example. We can choose such linear form on our vector space because this is what we can do. And if we choose, because if A divided by B is not in Q, this means, just to make sure, this means that they are linearly independent over the vectors over Q in this vector space. I mean, this is just an observation that if A over B is not in Q, then A cannot be written as A plus QB, right? So this cannot be 0, right? This means that they are linearly independent. And now we choose linear functional such that L of A is 1 and L of B is minus 1. They are linearly independent, so we are free to choose on the basis, right? This is just what we use. And if we choose it this way, then this product will be minus 1 because this is 1 times minus 1. But if we apply this decomposition and use the fact that these are all squares, we need to apply the same operator, but now on, I'm missing indices CI here. We need to apply this linear operator on the same numbers. But whatever these numbers are they rational, are irrational, whatever these numbers are, we know that this is actually some real number squared. Because we suppose that we can decompose everything into squares, and then using this bilinear functional, so again, we can see that if we chose just a bilinear form, which is area form, which is just a product of these two numbers, we would not get a contradiction. We would get 1 is equal to sum of squares. But if now, because of this linear independence, we can choose separately some bilinear form for which we have this L of A is 1, this is minus 1, and we get a contradiction. So we actually use the fact that by this decomposition, something more than just an area is preserved. Okay, and we just use the basic properties of tensor products. The fact that we can that they can be defined, and then we can choose a linear function on their dual. So just by using these two properties, we solve this non-trivial problem. Okay. Now we see that these very interesting properties are somehow essential to this problem. Okay. I do not know of any other solution to this problem without using bilinear forms in one or another way. Okay. Maybe you can use it explicitly like this or implicitly, but all the solutions that I know use some bilinear form of similar form. Now I didn't know what the audience is going to look like, so I just put everything that is in my notes on the slides, but I will not go into this. This is a very similar problem, and this is a very famous problem. So maybe you heard about a list of Hilbert's problems, like back in, I had to check history, sorry, I think at the beginning of 20th century, Hilbert wrote a set of problems to somehow to direct mathematics into interesting problems. So we would like to understand these things better. And his third problem, like one of the most fundamental, was the following problem. Now, let me introduce the problem to you. There is a simple observation, not that simple, but I'm sure that you all can solve this, that if we have two polygons of the same size, this is not obviously of the same area, right? This area is much bigger, but suppose that these two now have the same area roughly. Then, as a homework problem, you can find the composition of this rectangle into some triangles or something, whatever you choose. I'm not going to give you too many hints. That you can decompose this. Let me just make everything triangles. You can decompose this polygon and rearrange these pieces and turn them into this polygon. This is a nice problem for mathematical competition, say. Okay, this is a well-known result. You can try to solve it as a homework problem. You just need to be okay. Think about it. Okay, I'm not going to give any hints. This is well-known. So, like very natural, not generalization, but very natural question is the same true in 3 dimensions? Like, can we decompose each two bodies of the same volume, one into another? And now if we have a cube and, for example, tetrahedron of the same volume, is it possible to decompose this into this? And this was the question of Hilbert's third problem. And when you start to think about this problem, you see that something seems odd. That these angles between two faces are somehow impossible to get rid of. That these angles create you some problems to form such angles into cubical angles. So all these angles are 90 degrees, and this is something very weird that will be displayed on the next slide. But there is some motivation of using something similar to the previous problem. We saw that tensor products can help us to prove that something is not decomposable into something else. Now we try to use the same trick to solve this problem. So this is the idea of a mathematician, a student of David Hilbert, if I remember correctly. It's Max Dehn. He solved this problem, I think 3 years after Hilbert posted it. So this is Hilbert's third problem. It was a very famous problem, and he managed to solve it. And what he chose to do, he did very similar thing. He used this kind of expression, where this is a length of each side. He multiplied with some functional, depending on this angle alpha. We call it dihedral angle between two faces. And now bilinear forms of this type can give you contradiction in a similar way. Okay. So, but this is the example of the same type as the previous one. So I'm not going to go into too much details. I can if we have a bit more time at the end. But similarly to the previous result, we can show that this cannot be decomposed. And the correct angle is Arcus cosine of 1/3. So I don't know what that number is. But the point is that it is linearly independent with pi. Sorry. So this is the idea. Okay, what I'm going to say, I'm going to skip this because most of you haven't heard functional analysis, right? You did not have vector spaces or infinite number of dimensions and bounded operators on that. So I'm just going to skip this problem. This is a very nice application of tensor products, but this will be probably too hard to follow if you have never heard of a bounded operator. For example, in finite number of dimensions, each operator is bounded. But when you have infinite number of dimensions, not every linear operator is bounded. This means continuous, and it's a weird thing that happens only in infinitely number of dimensions, but I'm going to skip that because I wasn't aware who was going to listen to this talk. So let's go to something closer to you. In yesterday's talk, in the first talk of Professor Kovac, you already encountered this tensor power trick, but it was not obvious that this is actually again a tensor power. Okay, so as Professor Kovac beautifully explained, if you want to prove some inequality, x less than y, you can prove x less than c times y, and then if you can have some structure that implies x to the power of n is less than c times y to the power of n, you can conclude the first inequality. What this structure is, and this was implicit in Professor Kovac's talk, this is actually a tensor product in behind. So let's see again the same example. You all saw this yesterday. We want to prove AMGM inequality, and we can prove up to, so I chose a different constant, n over 4, just to have some simple number. If you don't know how to prove with E, this can be also proven by induction. And we can prove some weaker bound. So we can prove that left-hand side is at most 4 times right-hand side. And so how do we now use these tensor products that appear here very naturally? Professor Kovac yesterday introduced this thing. We defined geometric mean in any dimension and arithmetic mean in any dimension. Okay, so we just say whichever vector you give me, let's go to the next slide, you give me some vector, v1 up to vd, and I will say that geometric mean of this, so this is like a functional on all spaces that you have, something like universal property, but whatever vector you have, this functional can be defined. This is nth root of v1 times vd, okay. And also, you can define arithmetic mean of such vector as arithmetic mean of these numbers over d, right? So we prove, as we saw, that it's at most 4 times, and now we take any numbers for which we need to prove the EMGM inequality, and we raise it to a kth tensor power. We raise this vector to a kth tensor power. So we take numbers a1 up to an, and multiply this vector by itself k times. This is exactly what was done yesterday. Now you get all these things that appeared yesterday. Let me just show, for example, if we had numbers a1, a2, when we multiply them together using tensor products, then we get again the vector, which is of the form a1, a1. Then we need to place a1, a2, right? a1, a2. And a2, a2. Right, this is a tensor product of these vectors. And these are exactly expressions that Professor Kovac yesterday introduced, but it was like a miracle then. Now that you know tensor products, you can see that this is just a tensor product of a vector with itself. These are just coordinates of this kth power of a tensor product. Okay, and then when you apply these operator G of geometric mean and operator A, which is arithmetic mean, you get these expressions Professor Kovac yesterday explained. I do not want to repeat this counting argument, but you get the same expressions but raised to a kth power, right? So we define some functional on all the vectors that we can obtain, and then we say, okay, we know that it's at most 4 times, but now we take kth root and prove that this 4 can be removed. So again, what is behind is actually just a tensor product of a vector with itself. Okay, so all these weird properties that we had and this weird multiplication of 2 vectors that appears results in very interesting applications. Okay, so all these things just give you another tool in your toolbox of solving problems. So try to do something, prove some type of inequality with whatever constant you can, and then try to tensor power your result in some way. As you saw yesterday, sometimes even graphs can be tensor powered with themselves. So this is like a nice thing to have in mind. Whenever you can prove something up to a constant, try to tensor power everything and to improve the constant. Sometimes this will not work. If this constant depends on the size of the vector, this will not work, because by tensoring you will get power of this constant, and this cannot be reduced. But the main point is that these g's and a's, we could prove that g is 4 times a independently of the number of variables. So when we tensor power our vectors, we can see that this 4 can just disappear. Okay, so but if we could prove that g of v is 4 to the power of d, where d is size of v, we could not use the tensor power trick. It would just multiply, and it would not give us anything more than we already had. Okay, I hope now that this trick of using AMGM on these numbers is not that miraculous, now that you saw tensor powers. Okay, are there questions about this? Okay, great. The next problem that I want to discuss is one beautiful application of tensor power trick, from where I learned this trick, and probably Professor Kovac. This is like the best toolbox of mathematics that you can find on the internet. This is a blog of Professor Terence Tao. He's a Fields medalist, and he shares his knowledge on his blog. And this is one of his blog posts. It's actually a very nice result that reproves some old bound using this tensor power trick. Okay, so let's introduce the problem. So all of you that listen to linear algebra, and I believe that's everyone, you know that if you have R3, how many orthogonal numbers in R3 you can have? This is a simple question. Mutually orthogonal, right? Can somebody answer? 3, right? Yeah, this is a basic linear algebraic problem. You can have, let's call it use U1, U2, and U3. By using elementary linear algebraic properties, we know that we cannot have more than 3 mutually orthogonal numbers. What if I tell you, okay, as in machine learning problems, you do not actually care, and also in numerical linear algebra, like if some dot product is less than 10 to the power of 10, it's basically 0, right? Or 10 to the power minus 50. If something is very small, then it's almost orthogonal. And now we can say, oh, if I can prove that the things are almost orthogonal, I can have a good bound on this number of these vectors. You would suppose that, right? If I can prove that my if some vectors are mutually at most epsilon almost orthogonal, then we cannot have many of them, right? You can try to do that in your work, try to prove that, okay, this is less than 10 to the power of 10, and these are orthogonal, and we now know that we can have at most n of such vectors in the space R to the power of n. And this is where our intuition about high dimensional spaces is very wrong. So the thing is that very high dimensional spaces are very counterintuitive. So whatever you expect to have, you should check not twice but 10 times. So your intuition is completely wrong until you start to get more intuition by solving many problems in high dimensions. So let's introduce formally this problem. As you can see, we say that 2 vectors are almost orthogonal. We have 2 unit vectors, so we have a unit ball, and we pick some vectors, and we say they are almost orthogonal if their dot product u times v is less than, by absolute value, less than epsilon. And now the question is how many almost orthogonal vectors we can have in Rn, depending on, of course, on this epsilon. Of course, we can have n mutually orthogonal vectors because we can have any n orthogonal vectors. However, we would like to see if we can have many more, and this is where our intuition is very wrong. If I tell you now that you can pick vectors u1, u3, and u1, u2, and u3, such that u1 times u2 is less than 1 over 100, how many of them you could pick? And the answer will probably be, I haven't checked for these exact numbers, but the answer will probably be 3 again. Okay. But if I give you the same question, but not in 3 dimensions, but in r to the power of n, where n is extremely large. Let's say n is 10 to the power of 9. A billion, say. And I tell you how many of these vectors you can choose with dot product at most 1 over 100. It's like very small number. And the very counterintuitive result is that, I'm not sure if it's written here. Yeah, it's the theorem here. That you can choose almost exponentially many vectors which are mutually orthogonal. And this is very counterintuitive, right? So number goes from n to e to large power, to some small power, e to some small number times n. With this number, of course, depends on epsilon, because if we choose epsilon to be 0, then we cannot prove that we can have exponentially many of them. Yes, c is absolute constant.
Does it depend on n?
Yes, yes. So,
just when you're explaining the significance of this result, say for practical calculations, then one should add that today we want to do calculations in low precision. So epsilon is getting actually larger and larger and larger, and then it's getting larger and larger and larger too. So 10 to the power of 9, you will solve on a GPU, and your epsilon will be 10 to the power maybe 4 or 8 or something. So not 16.
yeah.
Or actually very far away from 16. So it actually has an added significance on today's hardware.
Yeah, that's correct. So this is also behind reasoning. I'm not an expert anyhow in neural networks, but this is like one of the reasons why neural networks work so well, even for small sizes. Because 2 things in neural networks are very different. For example, say cats and I don't know, these trash bins. Okay, they're very different in neural networks because their position tends to be almost orthogonal. And so now if we have n-dimensional space, we cannot encode only n objects in our surrounding. We can actually encode exponentially many objects in our surrounding. So when we increase the network size by 10 times, it's not like we're going to have 10 times more objects that we can describe. We will have exponentially many more objects that we can describe. And this is, as experts say, one of the reasons why neural networks work so well with such a small sizes compared to the number of things that we can observe around themselves. So the quick proof of this is like another very nice trick that you can try to employ in your problem solving, is when you have to choose something, find some construction, but you don't know anything how to start, try to throw things randomly. Okay, this is like the first strategy that you should start to work with. Like, I don't know any concrete example, but let me see what happens if I throw everything at random. So what happens in this case, and this is all expanded in details in my lecture notes, but if we take a large ball in n dimensions, and suppose we choose n vectors, n points on this ball, totally at random, so uniformly at random. You pick any vector on this ball, and we pick n many of them. Okay, this is like a standard trick started by Erdos, which Professor Kovac mentioned yesterday. This is like a random construction. So we pick n points at random, and we want to study what are the chances are that I fail. So what is the probability that, so I have vectors u1 up to un, and I ask myself, what is the probability that there exists some j and k such that uj dot product uk is in absolute value greater than epsilon. Okay, so if we call this event ajk, then this is probability of a union of jk go from 1 to n, ajk, and we can bound this trivially by the sum of probabilities, right? Probability of a union is bounded by a sum. up to n, probability of ajk. And how many elements are in this sum? There are roughly n squared elements, so this is roughly by n squared times probability of ajk. And now we want to estimate the probability that two random vectors, the two vectors chosen completely at random, have dot product greater than epsilon. And what actually appears is that this probability for any given epsilon is unbelievably small. Like, this is counterintuitive for our brains. So probability that u times v is in absolute value greater than epsilon is less than some constant times e to minus 1/4 n t squared. Sorry, not t, this is epsilon. This is epsilon. I usually do it with t here for some number, but this is actually the probability that two vectors independently chosen at random have dot product greater than epsilon is very small. We would like to try to grasp this thing by having any intuition, but it's really hard to gain any intuition in multiple dimensions. But actually what happens, sorry, I could draw a new ball. What happens actually in many dimensions is the fact that if I cut my n-dimensional space, so what it means that their dot product is greater than epsilon, this means that I can choose some level here and draw this parallel plane here and here. So what is the probability in n dimensions that my vectors lie here? Right. This will be some circle and in this region. Okay, this is equivalent, basically equivalent when you do conditioning. Conditional probability, this will be what you get. Everything is expanded in details in the note, so you don't have to worry. So what actually happens in large number of dimensions, almost all of the surface area of a sphere concentrates highly around the equator. So almost all of the area of a large ball lives inside around the equator. And this is counterintuitive. In 3 dimensions, it's just some fraction, but in multiple dimensions, most of the area lives inside of this small, whichever epsilon you choose. So this is epsilon, this is very small. This is not large, this is very small. But when you increase the number of dimensions, the fraction of the area which is not in that part of around the equator is exponentially small. This is very counterintuitive, at least for me. And now, because of this, we can insert this bound here, and we can, if we insert this bound here, then if I call this expression, let's say A, probably A is not a very good choice because of this AJ case, let's say expression E, then E is less than a constant times, this could be expectation, right? Again, very stupid choice. What? Sorry? It can be epsilon, yeah. I'm very, very bad at this. Do you have any better choice? I don't know. I will denote this. Let's say triangle. Okay, this is okay. So this triangle is less than c times n squared times e to minus 1/4 n times epsilon squared. And if I could prove that this is actually less than 1, what this would mean? This means that if I choose something at random and my probability of failure is less than 1, this means that there exist some chances that I win, right? So this means that if I could rewrite laws of physics or mathematics, and if I could really choose things somehow to increase my chances, that I could really choose something to win, right? If you have probability of 10% of winning in a lottery, that means that there is exactly that there exists some ticket which is winning ticket, right? This is what we use, and this is probabilistic method. So if we choose n to be this number here, some very small constant c1 times e to 1 over 8 n epsilon squared. Then when we square this, we will have 1 over 4, which will add to this. And if this C1 times C is less than 1, we will have a proof that this is less than 1. So if we throw everything at random, we will succeed. Okay, and we can choose n to be roughly this large. So this is basically the proof that one can do this. So now the question is this an optimal bound? Could we choose much more vectors, more than this? So the good way of studying this is in terms of, so we've seen that actually this means that this is a Gaussian distribution where the standard variation is of the size n to minus 1/2. This can be read like this. This is a Gaussian distribution, Gaussian tails, with standard deviation of n to this power. So we want to study everything on this scale, n to minus 1/2, and we can ask ourselves how many vectors can we choose whose dot product is at most 10 times what we expect. Okay, this is like a correct scale to study the problem. And the answer is that if we repeat the same calculation, that we can choose polynomially many vectors that are like 10 times bigger than expected size. This logarithm appears here with this random construction, but we can be more clever, and if we use something called Gaussian sums and real estimates in number theory, we could actually remove this logarithm. So the statement could be here, could be written as this, but we would need some number theoretic construction. So it's obvious that if we throw everything at random, we will not get the best bound. You do not solve Rubik's cube by rotating it randomly, right? You try to find some clever way, and if we find a clever way, this logarithm can be removed. And now, if we compare these two theorems, what they say. So if we remove this logarithm in a clever way, and logarithm is actually a very small number, so we do not have to remove it in our heads. We can say that we can choose polynomially many vectors with these mutual dot products, and is this the best we can do? And this is Kabachansky-Levenstein bound, but with a proof of Tenens-Tao. He proves actually with some different power that this is actually the best we can do. That we cannot choose more than polynomially many vectors with mutual dot products of size a times what is the expected variance, standard deviation. Okay, if we can think about this problem, this is a very, very nice result. So this is optimal. What we did randomly, almost randomly, what we almost happened to achieve randomly, and what we can achieve with number theoretical constructions using characters is actually the best we can do, up to some different power, but polynomially is good enough for us. So how do we prove this thing? I don't have much time, but we first use some linear algebra to prove that if this epsilon is very small, for example, if epsilon is 0, we need to have bound n, right? We cannot choose more than n numbers that are mutually orthogonal. 0 is mutually orthogonal. But if this epsilon is very, very small, like n to minus 100, we expect that it should behave the same. So we need some linear algebraic consideration to prove that there are at most linear number of them if epsilon is very small. Okay, so if epsilon is 1/2 of the expected random size, expected standard deviation, then we can choose at most linearly many vectors, maybe twice more than we can choose the number of orthogonal vectors. This must be some linear algebra in behind, because if epsilon is 0 in this bound, we get exactly n. Okay, so we need to have some good bound using linear algebra. And what's the trick? Okay, if we want to study dot products, then we can form a Gram matrix of all the dot products, and rank of this matrix is at most the number of dimensions. All vectors live in n dimensions, so this rank cannot be greater than n. And if we choose eigenvalues, then we can get such bound. So let's just go quickly through this. What's the main point is that if we want to study all the squares of these distances, this is actually the trace of such matrix. This is a very clever trick. I don't know who first employed this, but it's this is a well-known result, I think, by Noga Alon, if I'm not wrong. This was published by him, this result. So this is the trace of such matrix. Now we use the eigenvalue formulas, and we use Cauchy-Schwarz inequality. And from one side, we can bound this trace in one way, and from the other side, we can bound it in another way. But this is just only linear, very clever, but only linear algebra. So the main point is where we use the fact that this rank is less than n is in this Cauchy-Schwarz inequality that at most n eigenvalues will be different from 0. This is just where we use it. But I will let you to read this. You have to be careful to study this short proof. It's very clever, but it's short and it's linear algebra. What I wanted to say is that we can, so we have, what we want to concentrate on is this fact. So if epsilon is very small, we have at most linear bound. And now we want to prove the same thing for larger epsilons. And this is, as before, we want to enrich our structure by using tensor product. So if we apply the previous lemma to the kth tensor product of the vector with itself, as we already saw in the case of AMGM inequality, so now it is a natural trick to try, then we can get such bound. First, let me comment on this bound. If we just observe that this number lives in R to the n to the power of k because of the tensor product structure, then we would get a poorer estimate. But another trick that we want to apply is the following: that if we study more carefully these kth powers of each vector, so if we want to expand this expression, then we see that when we multiply this out, these are just expression in the basis. We see that when we expand everything out, the coefficients in front of these basis elements are the same if the number of elements that have 1 appearing are 1 times and 2 are 2 times and n are n times, these coefficients will be the same. This is just computation, like just observe this thing. So we can actually collect these things with, we can collect these things in a clever way. So if we take all these coefficients that are the same in front of some expressions, we can collect them and call this sum of these expressions as one single expression. And this will be a symmetric vector. Okay, because when you permute these things, this thing will be invariant to permutations. So this is, I'm a bit late, so I cannot go into too many details, but the fact is that, so when we just collect all these things in front of these basis vectors and we call this thing by its name, then this is called a symmetric power of tensors. And this space is obviously smaller than the set of all tensors that are, and its dimension is exactly this. This is just a simple counting that you can all do by yourself. And now if we choose k in a correct way by choosing some constant times a times squared, we get the claimed bound. So the main point was to prove some good bound using linear algebra and then tensorize everything that you have. And then have another very nice observation that this is not just any tensor, but this is a symmetric tensor. And the space of symmetric tensors is smaller than the space of all tensors. For homework, you can see what happens if you just consider this as any tensor. You would be able to enlarge epsilon up to 1. So we got the bound for epsilon less than n squared divided by half, and it will explode when epsilon goes to 1. But when we tensor, we would increase this to, n to minus 1/2 over 2. And now we can increase this to n to minus 1/2. So we enlarged our set of epsilons, but not by much. But if we employ this clever trick, then we can enlarge this set of epsilons up to the claim, which is square root of n, which is like how many of vectors can you have which are most 1/2 of dot product with each apart. So this is the largest that we can get, actually. Okay, so tensor product gave us this possibility. Sorry for going a bit too long. That's it.
Thank you, Alexander. Are there any questions from the audience to Alexander?
No, sorry.
Okay. If no questions, then thank you so much, Alexander, for a great lecture. And now we'll be moving to another one. I would like to invite to the stage Dr. Ilya Gogic, Associate Professor at the Department of Mathematics of University of Zagreb, specializing in algebra and analysis. And the topic will be elementary operators on matrices. Just a second. Our technicians will install the microphone.
Okay, am I set up?
Thank you, Ilya. So please take the floor.
Thank you. So where are the first slides? Oh, I see. Well, so far we survived many lectures. I hope you will also survive mine. So I'll talk about elementary operators on matrices, which is in fact a joint work with my ex-PhD student Mateo Tomašević. He recently obtained his PhD, defended his PhD thesis. This is, just briefly, this is another perspective how to represent tensor product, which Alexander already talked about. So let's start with some very easy definition. So assume we have a ring or an algebra, and we want to define basic maps which only involve operation characteristic for the ring. So in ring we have addition, we have multiplication, okay? Which form of maps can you produce using only these operations? Well, finite sums of two-sided multiplications, okay? So by definition, an elementary operator on a ring or an algebra A is a map phi from A to A, which can be expressed as this simple form. So as this simple form. So phi of x is nothing than the sum of finite two-sided multiplication maps. And these are called, this class of maps are called elementary operators. I'll just spoil a little bit on here, because elementary operators, the only thing what is elementary about elementary operators is their definition. Many properties about elementary operators are very non-elementary, okay? We will see. Well, in this setup, we will see. Okay. First of all, looking from the historical background, elementary operators are very important from algebra perspective, of course, and also in functional analysis. Moreover, we will see that they are also very important in quantum information theory. First of all, elementary operators comprise some very important class of maps, like inner automorphisms, given by this simple formula. Also inner derivations, like these commutators by a fixed element, or more generalized inner derivations when you have this form of maps, x maps to ax plus xb. Okay, so today elementary operators are very important in many branches of mathematics and physics, especially in operator algebras, where they play a key role when analyzing derivations, automorphisms, or more general completely bounded maps. Also finite rank perturbations, spectral theory, and so on, especially in the C-star algebra and von Neumann algebra setting. Also in ring theory, they are very important when studying maps which satisfy certain functional identities, especially in settings of prime and semi-prime rings. And also in quantum information theory, as we will see today, they, very briefly of course, because we don't have much time to go into details, the maps of this simple form, well, phi of x, so they act on matrices in this setup. So we have, let's say that goes to n times n matrices, given by this simple formula. Which satisfy this, the coefficients satisfy this property that the sum of the adjoint and A, and we sum over all indices, is equal to the identity. These maps represent so-called quantum channels in quantum information theory due to famous Choi-Krauss representation. So, I'll not deal with general rings or algebras. We are interested in specific ones like matrix algebras, because in matrices everything is, we can use linear algebra to get some nice result. But nevertheless, we want to define more abstractly, in more elementary operators, a more abstract setup. So first recall the definition of an algebra. So during this talk, F will be a fixed field. Mostly it will be complex numbers, but it can be any field. And we say that a vector space A over a field F is an algebra or associative algebra. If it satisfies, so first of all, we need to have some multiplication, and so multiplication needs to be bilinear and also associative, okay? So this is associativity and this is bilinearity. And we also assume that all algebras have identity elements, so we assume that algebra is unital, which means that it contains a unit element, which satisfies this simple property. Of course, if the algebra has the identity, it is unique. For any algebra, as for rings, we define the center. So what is the center? It is a set of elements which commutes with all other elements. It is denoted by z of A. And in the case when the center contains scalar multiples of identity, trivially this of course lives in the center. When the center is the smallest, like so only scalar multiples of identity, we say the algebra is central. Perhaps I'll put it on the blackboard to recall, because this will be very important when we want to generalize some aspects here. So A is central if the center of A consists only of scalar multiples of identity. We heard yesterday from Ivan's talk about ideals. I guess most of you all know what is an ideal, but let's also recall in this algebra setup. So a linear subspace I of A is called an ideal or two-sided ideal. It satisfies this simple property. So a vector subspace I of A is ideal. So if we multiply A, so this is from the right, we got inside I, and similarly from the left or the right, we got into I. Okay. We always have trivial ideals, which is zero ideal and the algebra itself. And if these are the only ideals in the algebra, we say that the algebra is simple. So A is simple. If the set of ideals are trivial, so are only ideals in A. And basically these will be only definitions we need. Also for an element A, then we can look the smallest ideal, which contains the element A. But this is called, we denote by ideal of A. This is just the sums of this form. This is the smallest ideal generated by the A. And in case, of course, if the algebra is simple, we only have two possibilities. Because when you take the A is 0, of course, we get the 0 ideal. When A is non-zero, it must be the whole algebra, okay? So if A is simple, for any A is A, so let's say the non-zero ideal of A is equal to the whole algebra A. Okay, and so we want to compare the algebra, so we have a category of when the objects are algebras, what are the appropriate morphisms. Of course, we must respect the operations. So a morphism in this category are homomorphisms, which respect, so they are linear, they are multiplicative, and they preserve identity. And if an algebra homomorphism is bijective, we also say it is usually said that it's algebra isomorphism, and then we say that algebras A and B are isomorphic. And we write like this. Let us first look some simple examples. So as you see, so this talk is on matrices. So by Mn of F, we denote the set of all n times n matrices over the field F, equipped with the standard matrix operations, standard addition, standard scalar multiplication, standard matrix product. Of course, this is an F algebra. The identity element is, of course, the identity matrix. This is n square dimensional algebra over F, of course. Because, of course, we have the standard basis. So for any two indices I and j, we denote by Aij the standard matrix unit, which is the matrix whose the position on Ij position is 1 and all other entries are 0. And of course, the set of all these matrix units form a basis of Mn of F. And we also have these simple rules when dealing with matrix units, these simple properties, how to multiply with elements. So, and we will exploit this during the talk. Okay? We have the first proposition, so that Mn of F satisfies both these conditions. It is central, it is simple. Okay? So let's see how to prove this. This is very easy, in fact, very easy exercise. So first we want to prove that it is central, so I mean, let's determine its center. So if we have an element A from the center of matrices, so it means that it commutes with any other element, especially it commutes with matrix units. When representing using this identity with matrix units, we get immediately that it is only possible, so if our elements of matrix are Aij, this is only possible that it commutes with all other matrix units if all non-diagonal entries are 0 and everything on the diagonal is the same. So basically what is this? So if an element is in the center of Mn of F, what we get is that A is nothing more than diagonal matrix lambda from some scalar lambda, which can be of course written as lambda times. Okay? So it is simple. It is central, sorry. The simplicity is also very easy because assume that we have a non-zero ideal I in matrices, and we have fixed some non-zero elements of some entries Ij is non-zero. And so what we have, we can express then this element, this multiple of matrix units as, of course, using the products of matrix units, it is the same as the product of these two diagonal matrix units with A. Now, this element is non-zero. We can divide it by the inverse. What we get then that the matrix units AKL for any KLN must be in the ideal. But of course, if all matrix units are in ideal, then everything is, because it is a subspace. So it is the whole It is the whole algebra, okay? And these two are the most centrality and simplicity important properties for matrices in this setup. Another example very similar to matrices is that, of course, we fix an arbitrary vector space over F, denoted by L of V, the set of all F linear maps. It is, of course, also an F algebra using the standard operation on elementary operators. And, of course, the algebra of linear operators is isomorphic to an anti-main matrices. How we get the isomorphism? Just to fix a basis. Fix a basis and then represent any linear map in this basis. Okay? So essentially these two algebras are the same. Any questions? Sorry.
You again chose some coordinates.
Of course I did. But I will have a universal property unlike you. Okay. Now go back. We are going back to our topic, elementary operators. Recall the definition. So an elementary operator on an algebra A is a map that can be expressed as a sums of two-sided multiplications. So, of course, this representation is far from unique. There are many, many other ways how to represent the same map. And what we want is the minimal possible representation, of course. And we define the length of an elementary operator as the smallest possible d, so that phi can be represented in this way. Yes?
No. Why is this called? Is this the same as rank? Why don't you call it rank?
On matrices, it will be. On different algebras, it's very non-trivial how to determine the length. This is a very good question because we will see during the talk. The centrality and simplicity will allow us to identify with the tensor product. Okay? And of course, we define that the length of the zero map is, of course, 0. So we are interested. Let's now work on matrices, very simple algebra, and find how to determine the length of an elementary operator. Okay? Okay, we have the first proposition. So it says it's very simple. So perhaps you can wonder, perhaps this is a very specific maps, okay? But on matrices, in fact, all linear maps are elementary operators. And this is what says this proposition. So any linear map on matrices is, in fact, an elementary operator at length as most n square. And this is a very simple exercise. I will just briefly get the idea. So we choose any matrix X. We represent it in forms of matrix units. So phi of X must be some other matrix. So its coefficients are, because of the linearity, is expressed as this sum. What do we do now? We just need to express what is f of matrix units, phi of matrix units, in terms of matrix units. So we decompose it in this sum. And what do we do now? We just plug it in back here. Okay? And we get two sums. Of course, I will not read it all. When we write it down in a convenient form, what we get, this sum is nothing more than, these are matrix units, this is X, and this is something which does not depend on X. This is independent on the variable, okay? It depends only on the operator phi. What we get? So we get the sum of, at most, n square two-sided multiplications. Okay. Was it clear? I'll try to skip some of linear algebra trivial details because you have everything in the notes. Okay. Moreover, the same can be the same. If you look the proof, this is not at all characteristic for matrices. This is true for any finite dimensional algebra. Okay, just pick a basis and do the same thing. So on any finite dimensional algebra, any linear map is elementary operator of length at most dimensions of the algebra. Okay. Now, as I said, we are going back to matrices again. And we have this simple lemma. So when is an elementary operator a zero operator? And you will see some very interesting correlation with Alexander's talk. Suppose that we have M matrices, A, I, and B, Y, from A to M, and B1 to Bm, which satisfy this simple, we satisfy this equation, so the elementary operator defined by these matrices is 0. Assume that the matrices AI are linearly independent. Then this equation forces that all BI's must be 0. Similarly, if you assume now that all BI's are linearly dependent, then of course the same holds for AI must be 0. Very similar like in tensor products. So, how we prove that? By induction. The base step when M is 1 is easy. So assume that A is non-zero. This means that one set containing one operator is linearly independent. So then we have that X, B is 0 for all X's. And now recall, MNF is simple. What does it mean? When we generate ideal with the A, we get the whole algebra, which means that especially there are some matrices, COI and DOIs, such that we can express identity as an elementary operator with this coefficients in variable A. Okay? And what do we know now? We plug it here. So we plug the identity. So then B is identity times B, which is now we plug what is I written this form. And of course, using this associativity, we get this simple sum, but by our assumption, all these products are 0. So this is 0. Okay? And then as what we wanted to prove that, then B is 0. Okay. In general case, we use, as I said, we use induction. I will not read all that. So we assume that our induction hypothesis holds for some M, and using the similar reduction, we get that the claim. Okay? I will say just one thing. We use in induction hypothesis, in inductive step, we essentially use centrality of the algebra, okay? Okay. This is so we have this property. So what about the second one? Of course, if we know the first one, then we know the second one. Of course, it is the same by the symmetry or just using the transpose. So it's trivial. Okay. Now we want to see, okay, we have two possible representation of an elementary operator. So assume we have these two representations, and we want to see what can we conclude. Well, so if we have this equality of elementary operators as a functions, which means that this equation is satisfied for all x. So if the set A1 to AM is linearly independent, then all BI's must belong to the linear whole or linear span of DI's. Okay? Similarly, if BI's are linear independent, then AI's must belong to the linear span of CI's. How can we see that? Easy, using, of course, linear algebra again. Simple. So, let's assume that AI's are linearly independent. We also have CI's here. What do? We look the subspace generated by all these matrices, so AI's and CI's. So it is certainly, because AI is linearly dependent, this subspace is certainly at the minimal dimension M. Of course, the maximum possible dimension is M plus R. So certainly there is some P between 0 and R, such that AI to AM, so we now extend it to a basis of this linear subspace, okay, generated by these matrices. What do we do now? Only thing we can. We express all coefficients C as the linear combinations of AI's. So we get sums like this. We now plug the sums in, so we represent a C case. So what do we get here? So we now put list on the left side. We express CIs as these linear combinations. We get these sort of sums. What do? We group, of course. We group first when the sum goes 1 to m, and the other when the sum goes from 1 to m plus p. So we get these expressions. And then what? Look, now here are AIs from 1 to m. Here are AIs from m plus 1 to m plus p. But this is linearly independent. What we learned from the previous lemma, this force is what? This force is that the right side is 0. Okay? Recall, we had by the previous lemma. Okay? And very, as you see, very simple. Okay. So we get that all these coefficients are 0. Something is clear. Okay. Okay. Of course, the other case follows similarly by using transposition. And now we can say what is the length of elementary operator matrices. Very simple. So if we have an elementary operator, it has a length m, d. So recall what is the length. So length, let's denote like L of phi is the smallest. So it's minimum of these, such that phi can be represented as for some I as MBIs in A. Okay, this was the length by definition. And on matrices, the length of an elementary operator is the smallest number of matrices which are linearly independent, so that phi can be represented in this way. Okay, so an elementary operator phi on matrices has length d if and only if we can find matrices AI and BI such that both sets of matrices AI and BI are linearly independent.
Can I ask a question?
Of course.
So what happens if you allow these things to become infinite dimensional, say X?
Oh, we will briefly mention it at the end.
I mean, I'm asking about...
No, you need to have some convergence then, because we can... I'll try to, if the time allows. It is a very natural question. We get some sort of approximation by completely bounded maps. We go into Hagerup tensor and so on. It's very interesting. So, very simple. So the length is just the... it has length d if and only if this... It means this representation and this set of matrices must be linearly dependent. Okay. How do we see that? Very easily. So suppose that phi has length d. Of course, if the length is 1, it is trivial, so assume that the length is at most 2. So phi can be represented as this sum for some matrices AI and BIs. And suppose that some of matrices are linear, this set is linearly dependent. What we do now, we express some matrix as a linear combination of the others. Without loss of generality, we can assume that this is AD. Okay, represented here. We plug, again, AD into the sum. What we get is an elementary operator of strictly less length. So we get this. So we get contradiction. Of course, the same holds for the set BI, so it must be linearly independent. On the other direction, so assume that phi admits a representation of this form where all coefficients are, the sets, corresponding sets are linearly independent. So if it has length less than d, so let's assume less or equal to d minus 1. So this means that we can represent phi as the sum of some other coefficients with at most d minus 1 elements. And recall by the previous lemma, what we get then? we get that all B1, Bi's must belong to the linear span of Di's. But this is impossible, of course, because they generate d-dimensional subspace, and this is at most d minus 1 dimensional, okay? So on matrices, to determine an elementary operator is very easy. So how can we determine it? First of all, let us say that, for example, if a phi is an elementary operator of length d, then any representation of the form when we have the sum with d summons are called minimal. Any such representation, okay? And now we see that then necessarily the condition to this to be minimal is these sets are AIs and BIs. These sets of matrices are linearly independent. Okay. It is also now clear that for any d from 0 to n squared, we can find an elementary operator of the length d. Okay, we just reduce. We choose the largest possible representation, and then we reduce the summons. Okay. Let's try to look at some examples. Of course, we always have to consider examples. One of the interesting examples here is a transpose map. I'm listening.
Why is it obvious that there exists elementary operator?
I will say now. First, we need to find the maximum possible representation. This will be the, for example, transpose. You will see now. So, we'll look at the transposition, okay? How we represent it as an elementary operator in terms of matrix units. So, phi of x is x transpose. What is x transpose? So, elements on the intersection of 8th row and j column is the element xjy. And now recall the standard products of matrix units. This is the same as the sum of the form aij x aij. Do you agree? And are the sets of matrix units? This is linearly independent. This is the basis. Mn of f. What does this mean? This means that this is an elementary operator of length, the maximum possible length, which is the dimension of matrices, which is n squared. Okay, sorry, how much time do you have, or do I need to stop? Sorry? 10 more minutes. 10 more, oh, okay. And do you see, Alexander, the answer to your question now? How do you produce any elementary? Just reduce the number of, just reduce the number of elements, okay?
How do we know that this one cannot be reduced?
Because of the previous lemma, these are linearly dependent. You cannot reduce it. Recall this elementary operator has length d, if and only if it meets the representation of with d summons, with all the corresponding set of matrices are linearly independent, okay? Let's look at another example. For example, this simple operator defined by phi of x is just trace of x multiple the identity, okay? This linear function, which is the trace multiple the identity. It is also, it's a very simple map, but it is also an elementary operator of maximal possible length, n squared. Why is that? So phi of x is a trace x times y. So what is this? So this is nothing but the trace of x times identity. So we have this sum, like here, okay? And now, of course, using the matrix units, we represented this matrix units, this multiple of matrix units is the same as aij x aji. Of course, the sets are linearly dependent, so this is also an elementary operator of rank at most n. What is interesting here, and we will see in the second part of the talk, that the transpose map is badly behaved map. Even though it is very simple, from many perspectives in this setup, it is very badly behaved. Okay, and now we can perhaps try to end this first part to see how we get minimal possible representations given an elementary operator, okay? Well, we start very naively. We choose an arbitrary representation of an elementary operator, okay? And then just using linear algebra. So if the sets are linearly dependent matrices, we are done. If not, we represent some summands as a linear combination of the other and repeat the process, okay? And finally, of course, we will get some linear independence, and this will be the corresponding length of the elementary operator. Is it clear? Okay. And now, of course, I'll use some auxiliary notation which will be very useful. How can we write elementary operators in compact form? So let's again start with definition. So phi of x is this sum. How can we write it in matrix form? We can write it like this. This is the same as the product of this row matrix times the diagonal matrix with x's on diagonal. And of course, then comes elements bui's. Okay? So if we say that the capital A is the vector, this is just auxiliary notation to follow, so it is the vector, the column AD. Define B is the column BY to BD. We can express it phi compactly as like this, A O dot B, meaning this. And how we get another representations of elementary operators? Well, very simple. Choose any invertible matrix. Okay, let's put it like this, A transpose, to be correct, okay? Because it acts, this is a row vector, okay? Row matrix. So this notation just means this action, okay? How can we get different representation of elementary operator? So, well, choose any invertible matrix. So in GLN, invertible matrix. And what we do now is just plug it here. So we plug it at the same thing. So it is the same as when we act in this way. So we plug matrix here, S, and plug S and minus 1. So it is the same as a transpose S dot S minus 1 B. This is the same because these sets are linearly independent, okay? This is the same using what is the inverse of a matrix. And in fact, any two minimal representations are implemented by some invertible matrix S of this form. And this is this proposition, but this is more compact form. Okay? So, if we have an elementary operator of length D represented in two ways, okay? Two sums of length D, so all sets of matrices are linearly independent. The statement is as follows, and there exists an invertible matrix S such that the coefficients Ci are nothing more than product of coefficients Ai's from the left in the matrix S, and similarly, dy's, we need, of course, take now the transpose because of this. So di's are the inverse, the transpose of the inverse, it is the same, it is the inverse of the transpose, product with the columns bi's. And how we prove that? Simple, very simple. Everything is simple. So, by previous lemma, we know that the coefficients Ai must be in the linear whole of Ci's, which means so this set is linearly dependent, so there are unique scalars. So for each I, there is some unique scalars Sij's, such that Cj is a linear combination of Ai's with coefficients Sij's. And in this way, we get an D times D matrix S with elements Sij. satisfying this equality. We now do the same thing, but from the right-hand side. In the same way, we get another matrix T, d-times 2 matrix invertible, such that di's are boi's from the left multiplied from t's. And now, of course, using the linear independence, it is very easy to see that S and T transpose are mutually inverse operators, okay? And we get so that S transpose times T is equal to identity. So all minimal representations are implemented in this simple way. And I think it is now natural to stop. Okay?
Thank you very much, Ilya. So after first part of Ilya's presentation, I would like to invite everyone for a short coffee break. We'll meet again in 20 minutes for part 2. So a little bit of refreshment and we'll come back. Thank you.
Thank you. Može. Naravno, i to ćemo raditi upravo sad. Da, da. Ti sam prvo sve jako i naivno raditi, bez ikakvih tenzora, bez ičega, a onda... Naravno, ali ću preko
是最赤裸裸的东西，它直接告诉我们的一个现象是背后的本质。
You know, mathematics is really something that once you understand it, you can see the beauty of it. You can see the kind of creativity. For some things, it's like art. If we think about everything surrounds the technology, the laws of physics that describe what happens in nature, we can use them, we can do something with them. We have the technology that we have because there is mathematics. Mathematics has been the way for the human to understand phenomena.
But in fact, by now there are many parts of mathematics which have become interesting for application. So many more than a few decades ago.
应用往往是综合的。even 在数学里面，你要解决一个应用数学解决问题，不是一个单门的理论数学可以解决，这实际上是一个系统数学的系统。
So we are at a moment where I think the computational power, it's really at the level, at the maximal level, maybe a bit better, but nothing exceptional. It's not going to be like 1,000 times better. And but mathematically, as I say, there are many challenges. I think once we will understand better how AI works, why it works, how to improve it, how to make it more efficient, safer, and everything, this is when we will see a next revolution.
If you have theory but without practical case, so you find, you kind of lose a sense of purpose. Whereas, here, if you do also the practice but without a good theory, well, you will continue on improving already known techniques, but you will not do something revolutionary. Of course, you will advance the technology, but basically you will be in the same trend. You will just add some new layer of refinement, but it will not be a step forward.
So we think that, of course, when you are a theoretician, you are looking for understanding. But when you are an engineer, you are looking for something which works better. But then there is the miracle that usually when you get better understanding, you become more efficient. So here, what we need is, in some sense, to enrich the amount of mathematical knowledge of the computer scientists we talk with, in order to make them realize that they can try to implement larger schemes.
就比如说是像那个大型模型，它里面最基础的一块是 transformer， 实际上基本来说90%以上都是矩阵。这些矩阵运算，我们如何给它加速？如果说我们做加进很多数学的东西，就比如说利用好的分解、向量分解，利用比较好的函数的设计，利用比较好那个位置编码方式，相信是可以更有效的去加速大型。
I studied mathematics. I developed new methods for solar physics. And then during conferences, I met people from cardiology. They showed their time series, their measurements, and looked very similar as solar activity. And then this is a way of interdisciplinary. Then we talked with each other and worked with each other. But the important point is each discipline has its own language, specific language. And the problem is that you have to learn, each side has to learn a bit the basic parts, not complete, but basic parts of the language of the others, that we really can communicate and that we can tell what are their real problems.
黄大年开始，比如黄大年可以提供一系列的数学课程，说是一些跟那个 AI 相关的数学，或者说跟其他方面，跟一些物理、跟材料化学都需要不同。最简单的方式是开始慢慢一步步的 的问题解不开来，真的就看兴趣，只要有一个好的一个提供，我觉得需要形成一个这样的机制。数学是最赤裸裸的东西，它直接告诉你的一个现象是背后的本质。
You know, mathematics is really something that once you understand it, you can see the beauty of it. You can see the kind of creativity. For some things, it's like art. If we think about everything surrounds the technology, the laws of physics that describe what happens in nature, we can use them, we can do something with them. We have the technology that we have because there is mathematics. Mathematics has been the way for the human to understand phenomena.
But in fact, by now there are many parts of mathematics which have become interesting for application. So many more than a few decades ago.
应用往往是综合的。even 在数学里面，你要解决一个应用数学解决问题，不是一个单门的理论数学可以解决，这实际上是一个系统，数学的系统。
we are at a moment where I think the computational power, it's really at the maximum level, maybe a bit better, nothing exceptional, not going to be like 1,000 times better. And but mathematically, as I say, there are many challenges. Once we will understand better how AI works, why it works, how to improve it, how to make it more efficient, safer, and everything, this is when we will see a next revolution.
If you have theory but without practical case, so you find, you kind of lose a sense of purpose. Whereas, here, if you do also the practice but without a good theory, well, you will continue on improving already known techniques, but you will not do something revolutionary. Of course, you will advance the technology, but basically you will be in the same trend. You will just add some new layer of refinement, but it will not be a step forward.
So we think that, of course, when you are a theoretician, you are looking for understanding. But when you are an engineer, you are looking for something which works better. But then there is the miracle that usually when you get better understanding, you become more efficient. So here, what we need is, in some sense, to enrich the amount of mathematical knowledge of the computer scientists we talk with, in order to make them realize that they can try to implement larger schemes.
就比如说是像那个大型模型，它里面最基础的一块是 transformer， 实际上基本来说90%以上都是矩阵。这些矩阵运算，我们如何给它加速？如果说我们做加进很多数学的东西，就比如说利用好的分解、向量分解，利用比较好的函数的设计，以及利用比较好的那个位置编码方式，相信是可以更有效的去加速大型。
I studied mathematics. I developed new methods for solar physics. And then during conferences, I met people from cardiology. They showed their time series, their measurements, and looked very similar as solar activity. And then this is a way of interdisciplinary. Then we talked with each other and worked with each other. But the important point is each discipline has its own language, specific language. And the problem is that you have to learn, each side has to learn a bit the basic parts, not complete, but basic parts of the language of the others, that we really can communicate and that we can tell what are their real problems.
黄大年开始，比如黄大年可以提供一系列的数学课程，说是一些跟那个 AI 相关的事情，或者说跟其他方面，跟一些物理、跟材料化学都需要不同最简单的方式开始，慢慢一步步的把这个问题给解剖开来，往真的方向走，就看你的兴趣。我觉得要有一个好的一个提供知识的平台，我觉得需要形成一个这样的机制。 数学是最赤裸裸的东西，它直接告诉你一个事情的一个现象的本质，背后的本质是什么。
And mathematics is really something that once you understand it, you can see the beauty of it. You can see the kind of creativity. For some things, it's like art. If we think about everything which surrounds us, the technology, the laws of physics that describe what happens in nature, we can use them, we can do something with them. We have the technology that we have because there is mathematics. Mathematics has been the way for the human to understand phenomena.
That, in fact, by now there are, in fact, many parts of mathematics which have become interesting for application. So many more than a few decades ago.
应用往往是一门综合学科。even 在数学里面，你要解决一个应用数学解决问题，不是一个单门的理论数学可以解决，这实际上是一个系统工程，数学的系统工程。
So we are at a moment where I think the computational power, it's really at the maximal level, maybe a bit better, but nothing exceptional. It's not going to be like 1,000 times better. And but mathematically, as I say, there are many challenges, and I think once we will understand better how AI works, why it works, how to improve it, how to make it more efficient, safer, and everything, this is when we will see a next revolution.
If you have theory but without practical case, so you find, you kind of lose a sense of purpose. Whereas, here, if you do also the practice but without a good theory, well, you will continue on improving already known techniques, but you will not do something revolutionary. Of course, you will advance the technology, but basically you will be in the same trend. We'll just add some new layer of refinement, but it will not be a step forward tomorrow.
So we think that, of course, when you are a theoretician, you are looking for understanding.
Session. Good. It's good. I really enjoy your one. I'm looking for what I really enjoy your engagement. Oh, thank you. It's really cool. I mentioned to Luca that I remember the old day professors that I was when I was studying, and sometimes they were like Animal Planet. They like falling asleep. No, you have. Okay, so we are ready to continue. Now Ilya will have his second part of his lecture, and this is the last lecture for today. So thank you so much, and please enjoy. Thank you.
Elementary operators from matrices to matrices. Arbitrary linear maps, then we show that they are elementary operators. Any operator set can be expressed as this sum. and then we showed what is the length of an elementary operator on matrices. L of phi is the dimension, so we look dimensions. So it is minimum dimension of the whole of AI's, dimensions of, this is linear whole of BI's. Okay? Very, very simple, how to determine the length. And now, which is natural, as I said at the beginning of my talk, that this can be viewed via the tensor products. And we'll do that now. And one thing I'm very cross at Alexander is that he didn't mention what is the most important property of the tensor product, because he's just an analyst and they don't like this. I'm joking, partially. Because the tensor products can be defined via universal properties. So what we know that we have tensor products of vector spaces. So we have vector spaces V and W over F, vector spaces over the field F. If we consider any bilinear map from V times W to, for example, some Z, vector space over F, there, of course, there is a canonical inclusion in tensor product iota. The universal property says whenever you have a bilinear map from V times W, there exists a unique, for example, phi, there exists unique phi bar such that this diagram commutes. Okay? The same holds for algebra. So if we start with algebras, they have additional structure, which is multiplication. We can, of course, define a multiplication on tensor product. How we do that? Very simple, using simple tensors. A tensor B times A prime tensor B prime is just this simple product A times tensor B time. Okay? This is well defined, and in this way, if A and B are F algebras, then their tensor product is, of course, also an F algebra. And it can be, of course, defined universally via universal property, because now we are working in a category of algebras, so linear maps are not sufficient. We need to also look homomorphism, algebra homomorphisms. So if, as before, by iota we denote the canonical bending of A times B into A tensor B, then the universal property says that for any F algebra C, whenever we have a bilinear map from A times B to C satisfying this multiplicative law, and of course identity goes to identity, the same diagram commutes, but now there exists a unique algebra homomorphism phi from A tensor B to C such that this diagram commutes. Okay? Well, when you need to prove something, some basic property of tensor product, this is the easiest part using the easiest way to use this universal property. Why is this important here? Because now we can identify the tensor product. Linear operator matrices are isomorphic to the tensor product of M and F with itself up to something. Up to something. We will see soon what. The proposition said because we need to look the reverse multiplication. Why is that? When you consider, for example, multiplication operator M B, similarly CD goes to CXD, and now we compose them. What do we get? So here is, of course, AXB, and now it comes CD. What do we see? It is reversed on the opposite side. Okay? It's reversed, like tensor product. Recall what on tensor product we have. A tensor B, A prime tensor B prime is A prime B B prime. Okay? we have we don't have this here. So we need to reverse. We need to transpose. What this proposition says that this natural map from this algebra, this is algebra tensor product to matrices given by this formula. So on the other variable we need to transpose is an algebra isomorphism. Okay. This is very easy to see using the universal property. So we define the map phi from the Mn of f times Mnf to linear operators on Mnf by this simple formula. 5ab on x is axb transpose, which is easily seen to, it is clearly bilinear, and it satisfies that it is multiplicative in this sense. Okay? And of course, identity goes to identity. So using the universal property of the algebra tensor product, there exists a unique map phi which satisfies this rule. And it is clearly surjective. Why surjective? Because all endomorphisms of my MNF are the elementary operators. So it's clearly surjective, and dimensions are the same. What is the dimension of tensor product? Recall? So what is that dimension of A tensor B? Do you recall? From Alexander's talk. Let's see if he did manage to bring the tensor products to you. Did you understand correctly? So, okay, it is the product of dimensions. Okay? N square times n square, okay? So we have the dimensions are the same. So it is surjective. Of course, it then must be injective because the spaces are the same dimension. So it is an algebra isomorphism. So we can identify Mn tensor Mn, okay, I'm writing usually Mn of f, with reverse multiplication. I will just put it here, with endomorphisms or linear operators on Mn of f. So as algebra isomorphism. So as algebra, these two guys are the same. What is the general, some larger perspective of this? Because of course in algebra we will like to see the general what's going behind all this. So we can generalize it as follows. Suppose that we have an F algebra, any F algebra A, and we define the opposite algebra A, circ. It is the same set, the same addition, the same scalar multiplication, but with opposite multiplication. So we define x times y is just y times x. This is in product in the algebra A. Okay? And then, using the same arguments as before, using the centrality and simplicity, so if the algebra is finite dimensional, central and simple, and recall, we only use that in all our proofs. Only these three. That the algebra is finite dimensional, that is central, it is simple. Using only these three properties, we can get in the same way that these tensor products of A tensor product with the opposite algebra is isomorphic to the linear operators on A. Using by this simple formula, so A tensor B goes to MAB, where of course MAB is two-sided multiplication. Centrality here is essential. Why? For example, if anybody consider this, so you can consider C, complex numbers, as an R algebra. Okay, we restrict to scalars to the field of real numbers. So what is the tensor product of C over R times C as algebra? This can be, well, perhaps this is an exercise. This is the same as, this is isomorphic to the C plus C. What do we see? This is no longer simple. Okay? This is a nice exercise to see why is that, okay? So this is no longer simple, so centrality is essential. What about simplicity? Is it also essential? Well, not really. It goes to the primus case. In general case, instead of simplicity, we can go to primus. We know what is a prime ring. The same is for algebra. So in algebra, A is prime. Whenever we have two ideals in A, whose product is 0, then one of the ideals must be 0. If the algebra is not prime, let's say that A is not prime. This means that we have two non-zero ideals whose product is 0. Okay? What do we know now? Very simple. Choose any non-zero element from I, any non-zero element from J. As a tensor, A tensor B, it is non-zero. Oh, it is non-zero tensor. But the corresponding, so this is non-zero in A tensor B, or A tensor A opposite, of course. But the corresponding map, the multiplication operator, which maps x to axb, these are ideals. Whenever we multiply these two guys, they are both in I and J. So this is 0. Okay? So we can see that primeness is essential. If we don't have a prime algebra, everything fails. And it is a nice result that primeness and so-called, well, not necessarily centrality, but something what you said that the algebra is centrally closed, that will not define, is sufficient also that converse is also true. Okay, so this is just from algebra perspective. Okay, any questions so far? And now I'll finally mention the most important part of this talk: some applications in, for example, quantum information theory. I'll try to be very brief. Does anybody have any experience with quantum information theory besides Mattia, who is teaching the course on or quantum computation, our faculty? Okay, so first let's fix the notation. It is usual, well, quantum information theory, in physics we use their the terminology, and so assume that H is a complex Hilbert space with an inner product denoted by this. If physicists usually assume that it is linear in the second variable, antilinear in the first, it's not important, but just mention that. And we adopt here the standard direct notation, Dirac notation, ket-bra, bracket notation. So the vectors in H in Hilbert space are denoted by kets, like this, bracket by this size. And the corresponding linear functional, recall by Riesz representation theorem, any bounded linear functional on if you call if you didn't hear anything about infinite dimensional spaces, forget it. On linear algebra, we know that on finite dimensional space, any linear functional is just a scalar inner product with a fixed vector. Okay, so the corresponding linear functional is denoted by this. So this is called bra. Okay, kets and bra. And they are combined. When we combine these two guys, we get the standard inner product. On the other way, when we combine like this, we get the rank 1 operator. Okay, rank 1 operator, how is defined? So this rank 1 operator maps phi to the inner product of psi 1 times inner product with phi along the vector psi2. Okay? This is the standard notation. For our mathematicians, it's perhaps a bit strange, but it's usual. If, in particular, if you have a unit vector psi, perhaps I can write it down on Blackboard because it will be important. So recall, so the cats, so H is a Hilbert space. So elements like this, psi. These bra vectors, and from the duals, which is standardly denoted by this, the dual of the, and then these two guys when we multiply, for example, like this, from one case to the, let's use the same notation, so we have psi2, oops. Oh, now I see. Okay, psi2, like this, then psi1 on phi maps to like the combination phi psi2 along vector psi1 along psi2, like this. So this is a rank 1 operator. In particular, when the vectors are the same, for example, psi is a unit vector, this is a rank 1 projection. Okay, and as usual for bounded, for B of H, we denote the algebra of bounded linear operators on H. Of course, in our setting, it will be just finite dimension. We don't need boundedness; it is automatic. And for any operator A, we denote by A star its adjoint. Physicists usually write A dagger, but I will not go that far. And we have the standard axioms in quantum mechanics. I'll just mention some very briefly. The first postulate says that to every closed quantum system, we can associate a complex Hilbert space H. A pure state of the system is represented by unit vector. So in this notation, it is this vector. Or equivalently by corresponding rank 1 projection. Okay? So these are the states. Or pure states. Or more generally, we can consider the mixed states, which are then represented by positive matrices of trace 1, when we have probabilities, denoted by usually by rho. And the second postulate say that what is evolution of quantum system, of a closed quantum system? It is implemented by unitary operator. Okay. So the evolution of a closed quantum system is described by this type of transformation. So the rho goes, the mixed states rho goes to U rho U star. This is the second postulate. Now we also have a postulate about the measurements. So I'll talk about generalized measurement. So the generalized measurement of a Hilbert on a quantum system, which is represented by a Hilbert space H, is just a finite collection of operators mk, satisfying this rule, so that this sum is identity operator. The measurement is called projective is if each operator mk is a projection. Then of course mk have mutual disjoint mutual orthogonal ranges, and the classical measurement is when it corresponds to the special case that all the mk's are projections of rank 1. So associated to pure states. So this index K labels all possible measurement outcomes. For example, if the system is initially in the state, pure state psi, then the corresponding probability of observing the, sorry?
I have a question. So first of all, these MKs are not Hermitian, right?
No, not necessarily in this sense. This is a general measurement when you have also.
Why is it not the other way around? MK star? Because you're saying the range should be orthogonal.
No. If these are projections, what I said, if these are projections, then they are self-adjoint in this case. Yeah? But not general. You don't have to.
You don't make a distinction between projection and orthogonal projection.
No. Yes, in no. In algebra, we have idempotents and we have projections. Projections are by definition are self-adjoint.
Okay, so because
Okay.
projections are by definition just idempotent.
Okay, for me, no. Okay, in this set, well, in C-star algebra set, they are automatic. We assume that they are, but yes, and thanks for asking. Okay, so if the system is initially in pure set psi, then the probability observed in the outcome k is just given by this simple product, inner product rule. Okay.
What is the definition of this?
So this operator acts on psi. This is vector, and then you take inner product with psi. And when you sum it with k, this is a positive, because this is a positive operator. This is a positive number, real number, between 0 and 1, because the sum of this operator is identical. So this is a probability distribution, okay, to observing the outcome k.
Just to get my mind straight, so this conjugation of nk is there because you're antilinear in the first argument, so when you flip n over to
Yes,
psi,
yeah,
you
yeah,
have
sure,
B
sure,
and the bra of
sure,
psi,
yes.
of n psi and then
Yes,
okay.
yes. Okay, and the final, I'll not go in all, just very briefly mention very important postulate. Then, of course, when we have some composite quantum systems, so we have quantum systems with associated Hilbert spaces H1 to Hm, we can consider the composite system, which is modeled by tensor product of these Hilbert spaces. So if the individual system is a pure state Cy, then the corresponding system, the composite state, is given by tensor product of states, of unit vectors.
If we have a simple state, do these H i's need to be finitely dimensional? Or?
We will be. In our cases, it will be. Okay? We will. Because in quantum computation, well, it is usual to take C2, to take H is C2 with basis which is like 0 and 1. So the orthonormal basis is 1 and 2. And then the qubit is just a linear combination, superposition. So the qubit is just written as this form. This is the standard orthonormal basis for, like this is the vector 0, 1, and this is the vector 1, 2. This is the standard notation, okay? And the corresponding qubit is in superposition of these two states when alpha squared plus beta is equal to 1, okay?
Is this C2 or is just C?
C2. C2. These are the standard canonical orthonormal vectors, okay? And this is the outcome when you measure the probability to get 0. This is alpha squared, 1 beta squared. So it is they must be equal to 1, the probabilities, okay? Okay. So for our mathematicians, what is a more natural framework to the notation? Of course, when we will deal with finite dimensional cases, then so we identify vectors with column matrices. So the inner product is just given by this rule, product of matrices. Of course, this rank 1 operator is nothing than the product of these two matrices. Okay, this is a row, then this is a column, this is a row matrix. Okay. Okay. A matrix, we know what is a positive semi-definite matrix. Usually it is just called positive. So let's recall the definition. A matrix A is said to be positive or positive semi-definite if it is self-adjoint and the inner product of x with ax is always non-negative. There are several equivalent definitions how to define positivity. One of them, so it is equivalent. A is positive, A is of the form T times T adjoint form time T, and also using the spectral theorem that A is self-adjoint and all eigenvalues are non-negative. So by the spectral theorem, what this means, any self-adjoint matrix, of course, can be, or more generally, normal matrix can be written then as a sum of corresponding projections, linear combinations with eigenvalues. In this case, using this notation, means that there is an orthonormal basis Wk for the space, such that A is represented of this form. These are the eigenvalues. These are the corresponding rank 1 projections. and these are eigenvectors. These are corresponding rank 1 projections, and these are the corresponding non-negative eigenvalues. Okay. Of course, we can now plug. We can factorize because this is, of course, non-negative. We can write it this equivalently as we denote new vectors. So vk, which is the square root of lambda k times wk's, and then we can rewrite any positive operator of this simple form. Okay. This will be essential in what now comes, representation. And a map, phi, linear map on matrices to matrices, is called positive if it maps positive operators to positive operators. More generally, it is called completely positive if for every k, we can consider the amplified map phi k, which is just the tensor product of phi with identity on k times k matrices. Okay, so phi k is identity on k times k matrices tensor phi, which goes to from this tensor product to itself. This can be, of course, identified, recall from Alexander's talk, but he only worked with vector spaces. Of course, mk of C tensor Mn of C can be identified as, well, it's isomorphic, but it can be identified by Mkn of C, okay? So it makes sense what is positivity here. So it is completely positive. Each this amplification phi k is positive. Of course, we already said that the tensor product of Mks and Mns is naturally identified with first with block matrices, and of course, then by, which is, of course, it's amorphic to matrices with Kn entries via the canonical isomorphism given by Kronecker product of matrices. Okay. Let's write it here because to recall. So phi from MnC to MnC is Cp completely positive if for any k the kth amplification, which is just so identity tensor phi, it goes to mk tensor mn to mk tensor mn, is positive for each k. What is the basic, the most simplest example of non-trivial completely positive map? Well, fix any matrix A and the phi of x is ax a star. This is very easy to see. It is completely positive. Why? But first of all, it is positive, certainly. We choose any positive matrix, factorize it as tt star for some matrix, and what we have, phi of x is att star a star, which can be factorized as at times its adjoint. So it is clearly positive. Why is completely positive? Very similar. So we consider the kth amplification, phi k given by this. What do we have? Phi k of x. So on each coordinate, phi x, it is so on each coordinate it is a multiplication from both sides with a and from the left and a star from the right. And then this can be rewritten like this. So it is just a product, tensor product of identity with a. So a on the diagonal times the matrix times the adjoint of this. It has the same form as the original, but only on largest level, okay? So as we observed previously, so this is positive, and so for each k, for each k, this is positive, so it is completely positive. Okay, let me see how much time. Damn it. Okay, let's. The very important map, if you remember from the first part of my talk, I said that the transposition is badly behaved map. First of all, as an elementary operator, it is the largest possible length. But on the other hand, in this quantum information setting, it is not completely positive. Transposition is not completely positive. Why is that? Well, consider when it fails, the second amplification fails to be positive, okay? So choose any So consider this this matrix C denoted by a tensor product of Aij's matrix units. Of course, this corresponds to this 4x4 matrix, which is positive. On the other hand, when we act by transposition, these two guys are the same, but these two reverse. What do we get? We get the permutation matrix. But permutation matrix, these two are swapped. So determinant is -1. Okay? It has a negative eigenvalue, it's not positive. So transposition fails to be positive. Okay. And more generally, how then we get the completely positive maps? Well, as a finite sums of these two-sided multiplications when AK and AK star from the right. Okay. And so it is a natural question. So how do completely positive operators look alike on matrices? And where is the application in quantum information theory? I'll just very briefly say, because I don't have much time. Usually, we are assuming that we are working in some sort of closed quantum system, but of course, we have environment. So we have E, and this is our system S. Okay? Environment, we have some interaction. We know from the second postulate that we are assuming that, okay, they are now combined, they are closed quantum system. The evolution is given by unitary matrix. Unitary matrix goes to S to E. Okay? But we are now, so this is some interference from the environment, like measurement, like whatever, noise. But we are interested how to get the action on S. This is called the quantum channel. So this will be then from E is a quantum channel. I will define it mathematically what it is. How do we get it? So we get it as like this formula. So assume that our system is in a state of, let's say, rho S. Environment is in initial state E. So by this fourth postulate, the composite quantum system acts on a tensor product. So the tensor product HS tensor HE. And this is unitary now when combined, okay? So we have a unitary, so this is initial states, and now we have a unitary action. So then rho of A, what will be? So it asks unitary on combined, so rho S tensor E environment tensor U star. This is the evolution of the combined system. And now we need to take a projection on which coordinate on the system coordinate. This is given by partial trace. Take with respect to E. Partial trace with respect to E. And this will be evolution of the system S. For more details, we can talk afterwards because I need to finish the talk. What is interesting that, so any completely positive map is in fact the sum of this form, and this is given by the famous Choi and Krauss theorem. It says like this: so to any linear map from Mn to Mn, we can associate its corresponding Choi matrix, which is matrix like, so you act on the second term with phi in a representative tensor product, okay? So it is a matrix is Mn tensor Mn, or of course we identified with Mn square, okay? So this is very large matrix. And what this is called the Choi matrix. What is interesting is that we have this very nice result called the Choi-Krauss theorem, that the following conditions are equivalent for any linear map on matrices. First of all, phi is completely positive. The second, that this matrix, C phi, is positive. And the third condition is that there exists matrices AI such that phi can be represented as is in standard form. Okay. The proof is not difficult, but of course I need to finish the talk. I included it in my slides. I just mentioned one more thing. So that quantum channels, by definition, well, there are several definitions. I know, given this type of definition, but there, from a mathematical point of view, what is a quantum channel? A quantum channel is a linear map on matrices to itself, to the algebra of matrices to itself, which is completely positive, and it is also trace preserving. One can show that this partial trace is satisfy this property. Okay. So we obtain what do they look? So why positivity? First of all, why do we need positivity? Because first of all, positivity. So positive matrix, which are represented by density matrices, need to go to density matrices. Amplification, of course, the positivity needs to be preserved. So this is complete positivity. And trace preserving probabilities needs to be preserved. So this is some sort of intuitive point of view. Okay, and we have one final condition now. We know the representation of completely positive maps, but we also need another condition that it is trace preserving. But this is very easy. When is elementary operator trace preserving? Well, if an elementary operator is represented in the usual form, phi of x is equal to ax by, so it needs to preserve trace for all x's. This is if and only if this condition holds. So we reverse bi ai is equal to identity matrix n. Okay, this is how do we see this? This is very simple, because if it is trace, if this sum is identity, we use the usual property of trace. We immediately get that this implies that it is trace preserving. Conversely, assume it is trace preserving. So for any x, the trace of phi of x is equal to the trace of x. Okay, we plug the formula for the action of phi. We again use the trace condition from phi. What do we get? That the trace of this matrix must be the trace of this matrix times x. But recall, the trace, we divide Hilbert-Schmidt norm by the trace on matrices, okay? So this is inner product. This means that this operator here needs to be the identity. So the Choi-Krauss theorem now says, combined in, so quantum channel QC, if and only if phi of x is equal to this form d a I x a I star with the sum of a I star a I sum to the identity. Okay, so using elementary linear algebra, we recovered the theorem, and I think it is now natural to stop. There are many very interesting things here from both mathematical and physical perspective, but we will leave this for perhaps another occasion. Thank you very much for your attention, and thank you very much to the organizers for this wonderful event. We really enjoyed. I hope I was not too boring, but for some of us, and hope to see you again.
Thank you so much, Ilya. Thank you for your lecture. And of course, I would like to thank all of the presenters for the splendid presentations that we saw during these 2 days. And before we conclude, do you have any questions for Ilya for his presentation?
We can talk. After this,
yes, okay. Thank you. Thank you so much then, Ilya. And now, before we conclude everything, I would just like to say a few things. One is that when you will be leaving our workshop, please return the cards to the reception desk. And also, if you are willing to have a taxi that can take you to the airport, you can also discuss with the administration at the front desk. She will make a list, and then she will help you to organize some transportation for the for the airport. So thank you so much from my side. It was amazing. I really enjoyed all the lectures, even though I was in the background. I listened to it carefully. So thank you so much. And now I would like to invite Ms. Mei Ling to the stage. She will make some closing remarks. Mei Ling.
Thank you all. It's coming to the end. Time passes so quickly. But we have a little bit magic to capture all the great moments. We capture some great moments in a video. So let's go for the video. Okay. So this is the first workshop between Warsaw Research Center, Chaspark, and Zagreb University. I hope it's like a sprouted seed. It will grow very strong, and it will bear rich fruit. And in the future, we hope we can meet maybe in China, maybe in other countries in Europe. We hope we can together to develop theory and algorithm, apply theory and algorithm to industrial problems, and make the better, make a better world, make an intelligent world. Maybe we can first invite Professor Luca and our speakers to share a few words of this workshop.
Well, thank you for the invitation. As I have read, and as all you have read, this is a forum for the exchange of ideas in the academic, technological, and scientific research. And we did have all of that. In particularly the last talk is the easiest to remember. So we had applications in quantum theory, we had universal properties, we had many interesting problems to solve. I'm really thankful that this is the beginning of nice and hopefully fruitful and long collaboration. And I see it very important for University of Zagreb and Department of Mathematics that the reach of what we have done is going to be the world reach, and that hopefully you will enjoy and be able to profit from the lectures and the exercises. So it is do yourself. So exercises are there to be solved, and only then will you really be able to say you have mastered the presented theory. So thank you so much, and maybe Jeko can say also something.
Well, I'll be very, very brief. Once again, on behalf of all speakers, we're really grateful for this opportunity. It was a pleasure to be here in the Huawei Research Center, and we're also grateful to the Chaspark platform and Ms. Zhang for organizing everything, recording, broadcasting. Everything is so great, actually. Thank you so much.
Thank you again for all the speakers for such inspiring topics. And is our magic ready? Magic needs some time. Maybe we can take a final photo together first.